Hello, welcome back to Amrutasblink. Whether you are an MBA student trying to forecast market trends, or BBA, BSC students tackling business statistics, or BSC, BCA, MCA student diving into the logic of computational mathematics, there is one concept that ties all your subject together, that is probability. Yes, I know the moment we see dice, cards, complex committee in textbooks, it can feel like just another mathematics problems. But in the real world, probability is the secret sauce behind the risk management, digital marketing algorithm, data science algorithm, and even for your AI logic. Today, we are going to solve a series of high impact problems, the ones that always show up in your university exams also. We'll cover basics of dice and cards, then arranging words and sitting arrangements, that is problems based on permutation, problems based on combination like committee selections, or a joint probability tables that you will definitely see in your business data sets. So grab your calculators, open your notebooks, and let's make the sense of the number. Let's start with practice problems. A uniform die is thrown at random. Find the probability that a number on it is 3, greater than 4, or even. Now here it is a very basic variety of the problem, that is die problem, coin problem. So let's say here you throw a die. So now you are aware about the basic concept, that is what is an event, what is a sample space. So I will directly start with the solution. So now here when you throw a die, so there are total 6 possible outcomes. Which all outcomes we can have, that is in your sample space you can have 6 possible outcomes, that is 1, 2, 3, 4, 5 or 6. That means how many total number of outcomes are there? There are total 6 outcomes, you can say. Now, what is our first question? That we need to calculate the probability of getting 3. So, what is the favorable outcome here? So, getting a face 3 on the top face is our favorable outcome here. So, let's define an event. A is equal to 3. So, here total number of outcomes is 6, that is n of s is equal to 6, and number of favorable outcomes is just 1. Hence, probability of this event, probability of A is equal to n of A upon n of S, which is equal to 1 by 6. Hence, answer of your first question is 1 by 6. Let's move to second part of this question. Now we need to calculate probability of getting a number which is greater than 4. Now, how many possible outcomes are there in this particular event? You can have either 5 or 6, because we need to have a number which is greater than 4. Now here you need to ensure that whether in the question they have asked greater than equal to 4 or it is just greater than 4. Now here they have asked you greater than 4, hence we cannot include 4 and we can include only 5 or 6. So how many events or how many possible outcomes are there in this event B, which is 2, and hence probability of this event, second event probability of B is equal to n of B upon n of S, which is equal to 2 upon 6, and we can simplify it to 1 by 3. Now there is a third part of the question, that is you need to calculate probability of getting an even number. Now let's say we have an event C where we will get even number. So how many possible outcomes are there? You can have either 2, you can have 4 or you can have 6. Hence number of favorable outcomes n of C is equal to 3, and probability of C is n of C upon n of S, which is equal to 3 by 6 and is equal to 1 by 2. So for the second question, greater than 4, probability is 1 by 3, and for the third question, probability of getting an even number is 1 by 2. So I hope you have understood our first problem, which is a very basic one, but yes, you may have problems similar to this one in your exams. Let's quickly move to problem number 2. In a single throw with 2 uniform dice, find the probability of throwing 5 and 8. Now, in previous problem, we had only one die. Now, here there are 2 dice. So, total number of outcomes are obviously 36 because we have 2 dice. So, the possible combinations are 6 into 6, which is equal to 36. Now, what we want, which is our first event, so probability of throwing 5. That means whatever numbers are there on the top face of both these dice, the summation of those numbers should be 5. So, which all possible outcomes are there? You can have either number 1 on the first die and 4 on the second die. Then you can have the summation as 5. Or you can have 2 on the first die and 3 on the second one. You can have 3 on the first die and 2 on the second one. Or you can have 4 on the first die and 1 on the second one. So, we can define event A as 1 4, 2 3, 3 2 or 4 1. So, what is n of A? That is number of favorable outcomes in this event is 4. Now, n of S is already there, which is 36, and hence probability of this event A, that is probability of getting sum equal to 5, is n of A upon n of S, which is equal to 4 upon 36, which is equal to 1 by 9. Now, in the same way, we will calculate the probability of getting sum as 8. So, now here, how we will get the summation as 8? So, let's say on the first die, now we cannot have 1, because if we have 1 on the first die, then maximum possible number which we will get on the second die is 6. And then if we have 1 and 6, then we cannot have the summation as 8. So, we have to omit this one, and let's say we'll start from 2. So, on the first die you can have 2, and on the second die you can have 6. Then on the first die you can have 3, and on the second die you can have 5. So, similarly we will find out all the possible outcomes. So, 2 6 is first possible pair, 3 5 is second possible pair, then 4 4 is the third possible pair, 5 3 is your fourth possible pair, and 6 2 is your fifth possible pair. So, how many favorable outcomes are there? 5. Hence, n of B is equal to 5, and probability of this event B we will calculate with our regular formula. So, probability of B is equal to n of B upon n of S is equal to 5 upon 36. Now, we cannot further simplify this. So, we will keep our answer as 5 upon 36. Let's move to problem number 3. 4 cards are drawn at random from a pack of 52 cards. Find the probability that there are king, a queen, a jack and ace. 2 are kings and 2 are ace. All are diamonds. 2 are red and 2 are black. There is 1 card of each suit. And sixth and last question is, there are 2 cards of clubs and 2 cards of diamonds. Now, let's try to understand the given scenario. Let's say you have a pack of cards. Now, we are aware that a pack of cards has 52 cards. And from these 52 cards, we need to select or we need to choose any 4 cards. So, first of all, we will define a sample space. So, whenever drawing 4 cards from a pack of 52 cards, so how many total number of ways are there by which we can choose these 4 cards? Is here we need to apply the combination. Why we need to apply the combination? Because you can have, let's say, first card, then second card, then third card and then fourth card. Now, this is not an arrangement, but this is a selection, and hence we have to apply the combination. Now, what's the formula for combination? I will just write it here. So, NCR is equal to n factorial upon r factorial into n minus r factorial. So, now here when we need to select 4 cards from a pack of 52 cards. So here n is equal to 52 and this r is equal to 4. So number of events in the sample space is equal to 52C4. Now we'll further simplify this, that is 52 factorial upon 4 factorial into 48, that is 52 minus 4 is equal to 48 factorial. Now we need to solve this one. So 52 factorial we will split up to 48 factorial, so that 48 factorial will get cancelled. That is 52 factorial is equal to now 52 into 51 into 50 into 49 into 48 factorial. 4 factorial we will also split it down, 4 into 3 into 2 into 1 and 48 factorial as it is, so that this will get cancelled. We will further simplify this. So let's say this 4 ones are 4 and this is 13, this 3 ones are 3 and this is 17, this 2 ones are 2 and this is 25. So in the numerator we have 13 into 17 into 25 into 49 divided by 1, which is equal to 2,70,725. So how many possible events are there in the sample space is a huge number, which is equal to 2,70,725. Now we will calculate number of events in all the given questions, in all the given scenarios. So let's say our first scenario is there is a king, there is a queen, there is a jack and there is an ace. Now in order to solve all these problems, you just need to understand what is the composition of the cards in this well shuffled pack of 52 cards. So now we are aware that in a pack of cards there are always 4 kings, 4 queen, then 4 jack and 4 ace. Now we want 1 king, 1 queen, 1 jack and 1 ace. So how many possible favorable ways are there? So we can select a king from 4 kings, that is 4c1, then a queen from all 4 available queens, that is 4c1 again, a jack from all available 4 jacks, that is 4c1, and an ace again from available 4 options of ace. So 4c1 into 4c1 into 4c1 into 4c1. Now 4c1 is always equal to 4, hence we will have 4 into 4 into 4 into 4, which is equal to 256, and hence probability of this first event A, that is probability of having a king, a queen, a jack and an ace is equal to P of A, which is equal to N of A upon N of S, is equal to 256 upon 2,70,725. If you can further simplify this, but here there are no common factors, so we have to keep our answer as it is, that is 256 upon 2,70,725. Let's move to the second problem. There are 2 kings and 2 aces. Now we have already understood by now that there are 4 kings. So out of those 4 kings we need to select 2 kings, and out of 4 available aces we need to select 2 aces. So how many favorable ways are there, which is equal to 4c2 into 4c2. So now we will further simplify this 4c2 as 4 factorial upon 2 factorial into 2 factorial into, again second 4c2 is 4 factorial upon 2 factorial into 2 factorial. So this we will simplify as 4 into 3 into 2 factorial upon, now this 2 we will split as 2 into 1. I have not written 1 here, so it is just 2 into 2 factorial, and similarly for the second set 4 into 3 into 2 factorial upon 2 into 2 factorial. Now this 2 factorial will get cancelled, this will also get cancelled, so this 2 and this 2 is equal to 4, so this will get cancelled. So now in the numerator we have 4 into 3 into 3, which is equal to 36. Hence number of favorable outcomes, that is N of B, is equal to 36, and probability of B is equal to N of B upon N of S, which is equal to 36 upon 2,70,725. 725. This is your final answer, because here also we cannot further simplify this. Now let's move to third case, that is all are diamonds. So how many diamonds are there? So there are 13 diamond cards in a deck, and we need to select 4 cards out of it. So 13C4 are the favorable ways. So 13C4 is equal to now 13 factorial upon 4 factorial into 9 factorial. So this 13 factorial we will split up to 9 factorial, that is 13 into 12 into 11 into 10 into 9 factorial upon 4 factorial we will split 4 into 3 into 2 and 9 factorial as it is. So now this 9 factorial will get cancelled. This 4 3s are 12, so this 12 will cancel, and this 2 1s are 2, so this 2 5s are 10. So we have 13 into 11 into 5, which is equal to 715, and hence probability of this event C is equal to n of C upon n of S is equal to 715 upon 2,70,725 is the final answer. You can further simplify this, that is, now I guess you can divide this with 5. So 5 1s are 5. So 143 upon 54,145 is ideally your final answer. Let's move to fourth case, that is there are 2 red and 2 black. So let's say this is an event D where 2 cards are red and 2 cards are black. Now in a pack of 52 cards there are 26 red cards, that is diamond and heart, and 26 black cards in a deck. So favorable ways are 26C2 into 26C2, that is 26 factorial upon 2 factorial into 24 factorial into 26 factorial upon 2 factorial into 24 factorial. So we'll further simplify this. 26 into 25 into 24 factorial upon 2 into 24 factorial into 26 into 25 into 24 factorial upon 2 into 24 factorial. So this 24 factorial will get cancelled, and then this 2 1s are 2. So this is 13, this is also 2 1s are 2, and this is 13. So we have 13 into 25 into 13 into 25, which is equal to 1,05,625. Hence probability of this event D is equal to n of D upon n of S is equal to 1,05,625 upon 2,70,725, and you can divide this by 25, and the best possible fraction we will have as 225 upon 577 is the final answer. Let's solve the case number 5. There is one card of each suit. So let's say this is called as an event E, where there is a one card of each suit. Now there are 4 suits with 13 cards in each suit. So we can have one card from each suit in 13C1 ways. So 13C1 into 13C1 into 13C1 into 13C1, that is 13 into 13 into 13 into 13, which is equal to 28,561, and hence probability of this event E is equal to n of E upon n of S, which is equal to 28,561 upon 2,70,725. And then the last case of this example number 3, that is there are 2 cards of clubs and there are 2 cards of diamond. So let's say we have an event F where there are 2 cards of club and 2 cards of diamond. Now how many club cards are there? 13. And how many diamond cards are there? These are also 13. Hence favorable outcomes is 13C2 into 13C2, that is 13 factorial upon 2 factorial into 11 factorial into 13 factorial upon 2 factorial into 11 factorial, which is equal to 13 into 12 into 11 factorial upon 2 into 11 factorial into 13 into 12 into 11 factorial upon 2 into 11 factorial. So this 11 factorial will get cancelled. This 2 ones are 2 and 2 6 are 12. Here also 2 ones are 2 and 2 6 are 12. So we have 13 into 6 into 13 into 6, which is equal to 6084, and hence probability of this event F is equal to n of F upon n of S is equal to 6084 upon 2,70,725 is your final answer. This particular variety, that is problems based on the pack of cards, are can be asked in your exam. We have tried to solve all the possible varieties here in this particular example only. Let's move to example number 4. What are the chances that a non-leap year should have 53 Sundays? Now let's understand this scenario first. So to find out the probability that a non-leap year has 53 Sundays, first of all we have to break down the number of days during an year. So let's say how many total number of days are there in a non-leap year? So in a non-leap year there are always 365 days. Now focus on this part of the question, that is it is a non-leap year. If it's a leap year, then number of days are 366, but it is non-leap year, hence number of days are 365. Now let's say if we want to break down these 365 days in number of weeks, then we have to divide this 365 by 7, because there are 7 days in a week. So we will divide the total number of days by 7, that is 365 divided by 7. So in this way we will have total 52 weeks during an year and 1 day extra. Now let's understand, the 52 full weeks are there. That means during an year all 7 days are going to be repeated at least 52 times. So you are going to have 52 Sundays, you are going to have 52 Mondays, you are going to have 52 Tuesdays, and you are going to have 52 Saturdays as well. But because of this one extra day, the scenario is going to change. So during 52 full weeks means there are definitely 52 Sundays. Okay? Now along with the 52 of every other day of the week, one extra day is going to be there, and we need to calculate the probability of getting 53 Sundays. So the occurrence of this 53rd Sunday depends entirely on what is that extra one day happens to be. So how many possibilities are there for this one extra day? So that one extra day can be Sunday, can be Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. So how many events are there in the sample space? It is not 365, it is not 366, but that one extra day can be any day out of these 7 days, and hence n of S is equal to 7. Now for this extra day to be a Sunday, so we need to calculate the favorable outcome, that is for the year to have 53 Sundays, that is the extra day must be a Sunday. Hence number of favorable outcomes is only 1, so n of A is equal to just 1, and n of S we have already calculated, which is equal to 7. Hence probability of this event A, that is probability of having 53 Sundays in a non-leap year, is equal to n of A upon n of S, which is equal to 1 by 7. So I hope you have understood this specific variety of the problem based on the calendars. Let's move to example number 5. If 6 dice are rolled, then what is the probability that all shows different faces? Now we have already seen whenever we throw just one die, so how many total possible outcomes are there? That is 6 possible outcomes are there. But here in this question 6 dice are rolled, so when rolling a 6 dice simultaneously, the total number of outcomes are now 6 into 6 into 6 into 6 into 6 into 6, that is 6 times we have to multiply 6. That's why n of s is equal to 6 raised to 6. Now you can keep the 6 raised to 6 as it is, or you can write the exact number, that is 46,656. Now we need to find out the probability that all show different faces. So first of all, let's find out how many favorable outcomes are there. Now just try to understand this scenario first. For all the 6 dice to show different faces, each die must land on the unique number from the set of 1 to 6. This is equivalent to arranging the 6 distinct numbers in 6 different positions. That means ultimately we are doing permutation here. So let's say, for example, if the first die can be any number out of 6 numbers, then for the second die there are only 5 different choices. So let's say on the first die we have got 1. So second die can have 5 choices. Then the third die will have 4 choices, and so on. That's why number of favorable outcomes here are 6 into 5 into 4 into 3 into 2 and into 1. That means number of favorable outcomes is nothing but 6 factorial. So n of a is equal to 6 factorial, that is 6 into 5 into 4 into 3 into 2 into 1, which is equal to 720. And hence probability of a is equal to n of a upon n of s, which is equal to 720 upon 46,656. When we simplify this, we'll get it is equal to 5 upon 324. Let's move to example number 6. A bag contains 20 tickets marked with numbers 1 to 20. One ticket is drawn at random. Find the probability that it will be multiple of 2 or 5, and in second case it will be multiple of 3 or 5. So let's say there are 20 tickets in a bag. So in a sample space we will have all the 20 numbers, that is 1 to 20. Hence total number of outcomes in the sample space n of s is equal to 20. Now our first problem statement is we need to calculate the probability that it will be a multiple of 2 or 5. So let's say it is an event A. So multiple of 2, we can have the number should be multiple of 2. That is, we can have 2, 4, 6, 8, 10, 12, 14, 16, 18 or 20. And here it is multiple of 2 or 5. That's why we also need to include the numbers 5, 10, 15 and 20. But 10 and 20 is already there. That's why we will just include 5 and 15. Hence n of a is equal to 12, and then probability of a is equal to n of a upon n of s, which is equal to 12 upon 20, which is equal to 3 upon 5. Here only important part we need to understand is that the number should be multiple of 2 or 5. That means we have to include all the multiples of 2 within that particular range, and as well as we also need to include all the multiple of 5 because it is an OR operator. Now let's say we'll find out multiples of 3 or 5. Now n of s we have already calculated, n of s is equal to 20, and now let's say we have event B where the number is multiple of 3 or 5. So event B is equal to now 3, 6, 9, 12, 15, 18, and as well as multiple of 5. So we have to include 5, 10, 15 is already there, so we will not repeat, and 20 also. So how many events are there? How many possible outcomes are there? N of B is equal to 9, and hence probability of B is equal to n of B upon n of S, which is equal to 9 upon 20. Let's move to example number 7. An urn contains 8 white and 3 red balls. If 2 balls are drawn at random, find the probability that both are white, both are red, and one is of each color. How many total balls are there? There are total 8 and plus 3 red. That means total number of balls in that particular urn is 11. And how many balls we need to choose? That is, we need to select 2 balls. So the number of ways to select 2 balls from these 11 balls. Now we need to select, we need to choose. That's why we have to apply rule of combination here. So that's why total number of ways to select 2 balls from this 11 is given by 11C2, which is equal to 11 factorial upon 2 factorial into 9 factorial, that is 11 into 10 into 9 upon 2 into 9 factorial. Now this 9 factorial will get cancelled. This 2 ones are 2 and 2 5s are 10. So 11 into 5 is equal to 55. Hence we can say that n of s is equal to 55. Now let's move to first case, that is both the balls are white. So we will define how many outcomes are there in this event A. So we need to select 2 white balls. So how many total white balls are there? 8 white balls. That means we need to select 2 white balls from 8 available white balls. That's why favorable ways are 8C2, that is 8 factorial upon 2 factorial into 6 factorial, which is equal to 8 into 7 into 6 factorial upon 2 into 6 factorial. So 6 factorial will get cancelled. Then this 2 ones are 2 and 2 fours are 8. So 7 into 4 is equal to 28. Hence we can say that n of A is equal to 28. Now probability of this event, that is both are white, is equal to probability of A, which is equal to n of A upon n of S, which is equal to 28 upon 55. Let's move to second case, that is both are red. Now how many red balls are there? There are 3 red balls. So we need to select 2 red balls out of all available 3 red balls. So how many favorable ways are there now? That is 3C2, which is equal to 3 factorial upon 1 factorial into 2 factorial, that is 3 into 2 factorial upon 2 factorial. 2 factorial will get cancelled and hence it is equal to 3. Hence we can say that n of B is equal to 3, and hence probability of B, that is probability of both the balls are of red color, is equal to n of B upon n of S, which is equal to 3 upon 55. And let's look at the third case, that is one of each color. So one of each color, that means one ball should be white and another ball should be red. Now there are 8 white balls and 3 red balls. So number of favorable ways are 8C1 into 3C1. So 8C1 is equal to 8 and 3C1 is equal to 3. Hence 8 into 3 is equal to 24. So probability of this event C, that is probability of one ball of each color, is equal to n of C upon n of S, which is equal to 24 by 55 is the final answer for the third case. Let's move to example number 8. The letters of the word article are arranged at random. Find the probability that vowels occupy even places. Now this is a very specific variety of probability problems where we need to arrange letters of any particular word and we need to find different words from the letters which are available in that particular word. So let's understand this specific variety very carefully. You will definitely have at least one problem on this specific variety. The letters of the word article are arranged at random. Find the probability that vowels occupy even places. So let's understand the problem statement first. Given word is the article. So how many distinct letters are there in this word article? That is ARTICLE. So there are 7 distinct letters. Now if we observe carefully, no single letter is repeated. All these are 7 distinct letters. Now out of these 7 letters, how many vowels are there? There are 3 vowels, that is A, I and E are vowels, and there are 4 consonants, that is R, T, C and L. These 4 consonants are there. So first of all, let's calculate total number of arrangements, that is n of s. Now there are 7 letters. So since all the 7 letters are distinct letters and no letter is repeated, so total number of ways to arrange them is equal to 7 factorial. Hence n of s is equal to 7 factorial, which is equal to 5040. Now we'll calculate number of favorable outcomes. So what is a required arrangement? That is, vowels should occupy even places. Now how many vowels are there? There are 3 vowels, that is A, I and E, and we want these 3 vowels to occupy even places. So let's look at the positions available in this 7 letter words. So let's say I will just 1, 2, 3, 4, 5, 6 and 7. So let's say this 1, 2, 3, 4, 5, 6 and 7. Now how many even positions are available? This 1, that second position, 4th position and 6th position. These 3 even positions are available. And how many vowels are there? There are only 3 vowels. So exactly 3 even places are there, which should be occupied by 3 vowels. So in how many ways? So there are exactly 3 vowels will be occupying these 3 places, that is 3 factorial. So here we have to arrange 3 vowels in 3 even places. Hence total number of possible arrangements of these vowels is 3 factorial. Now there are 4 remaining places, that is 4 odd places, and these 4 odd places are to be filled with remaining letters, that is these 4 places are to be filled with remaining 4 consonants. So how many possible ways are there? 4 factorial. Hence total number of favorable ways, that is n of A is equal to now 3 factorial into 4 factorial. 3 factorial is equal to 3 into 2 into 1, which is equal to 6, and 4 factorial is equal to 4 into 3 into 2 into 1, which is equal to 24. So n of A is equal to now 6 into 24, which is equal to 144, and n of S we had already calculated, that is 5040. So probability of this event A is equal to n of A upon n of S, which is equal to 144 upon 5040, which is, you can further simplify this, so which is equal to 1 upon 35. So let's say this 144 and 5040. So you can divide this, let's say by 2. So 2 sevens are 14 and 2 twos are 4. Then this is 2, 5, 2 and 0. You can further divide this, let's say by 4. So 18 and 18 upon 630. So let's say we'll divide this by 9. This is 2 and this is 70, and then 2 ones are 2, and this is 35. So further by simplification of 144 upon 5040, you will get the answer as 1 upon 35. Let's move to example number 9. This is a exactly similar problem with a little bit variation. The letters, if the word failure are arranged at random, find the probability that consonants may occupy only odd positions. Now here let's analyze the word first. So in this word failure, there are how many letters? F, A, I, L, U, R and E. So 7 distinct letters are there. Now out of these 7 letters, how many vowels are there? A, I, U and E, that is 4 vowels are there, and there are 3 consonants, that is F, L and R. Now we'll first of all find out total number of arrangements. So since there are 7 unique letters, so and out of these 7 letters nothing is repeated, that means 7 unique letters are there. So total number of ways to arrange them, that is n of s is equal to 7 factorial, which is equal to 5040. Now let's move to actual required arrangement of the letters. So what we need to find out? We need to find out the probability that consonants may occupy only odd positions. So again we will create the structure. So how many letters are there? How many places are there? So first position, second position, third, fourth, fifth, sixth and seventh. Now out of these 7, how many odd positions are there? This first, third, fifth and seventh. That means how many odd positions are there? There are 4 odd positions. So the condition is that consonants must occupy only odd positions. So there are first odd position, third odd position, fifth and seventh odd positions. So there are 4 odd positions available, and how many consonants are there? There are only 3 consonants. Now in the previous problem there were 3 even places and only 3 vowels were there, but here 4 places are available, but there are only 3 consonants, that is F, L and R. So 3 consonants to occupy these 4 positions. So in how many ways 3 consonants can occupy these 4 positions is 4C3, that is 4 factorial upon 1 factorial into 3 factorial, which is equal to 4. Now once these 3 consonants will occupy any 3 positions out of the available 4 positions, so remaining 4 positions we need to fill now. So remaining 4 positions, that is 3 even positions, and this 1 remaining odd position is to be filled by 4 factorial ways, that is 4 into 3 into 2 into 1, which is equal to 24. So total number of favorable ways is equal to n of a, which is equal to 4 into 24, which is equal to 576, and hence probability of this event we can calculate n of a upon n of s is equal to 576 upon 5040, which is equal to 4 upon 35. Let's move to example number 10. 20 books are placed at random in a shelf. Find the probability that a particular pair of books shall be always together and never together. Now how many total number of arrangements are there? We need to arrange 20 books on a shelf. So total number of ways is simply 20 factorial. Hence n of s is equal to 20 factorial. Now how is the required arrangement? In first case, a particular pair of book shall all be always together. So we need to calculate probability of this first case. So let's say we group that particular pair. So we will tie any 2 specific books together and we will treat them as one single unit. So there are 18 individual books now, and plus this one pair of books. So how many total units are there? 18 individual books plus this one pair, that is 19 units. Now these 19 units can be arranged in 19 factorial ways, but these 2 books which are there, which we had considered as one pair, so they can interchange their position also, and hence these 2 books inside that particular pair unit can swap the places. So they can also be arranged in 2 factorial ways that is 2 factorial. 2 factorial ways, that is 2. And hence total number of favorable ways, that is n of a, is equal to 19 factorial into 2. And hence probability of this event, probability of a is equal to n of a upon n of s is equal to 19 factorial upon 2 into 20 factorial, which is equal to 19 factorial into 2 upon 20 into 19 factorial, and hence 2 upon 20, which is equal to 1 by 10. Now we will calculate probability for the second case, that is this particular pair of books is never together. So probability that a particular pair is never together. Now we will calculate this probability in a reverse way. So probability of never together is equal to 1 minus probability of these books are always together. And we had just calculated probability of these particular two books always being these two books always together is equal to 1 by 10. Hence probability of these particular two books are never together is equal to 1 minus 1 by 10, which is equal to 9 upon 10. Let's move to example number 11. N person are seated on a n chairs at a round table. Find the probability that two specified persons are sitting next to each other. Now, let's understand the question first. So, n people are to be seated on n chairs, but it is a round table. Let's say these n people, I will just assume that there are only 3 people, and these 3 people are to be seated on a linear arrangement. So let's say first one is here, second one is here, and third one is here. So these 3, when the arrangement is linear, then at that particular time we can calculate that in how many ways they can sit in this linear arrangement is 3 into 2 into 1, that is 3 factorial ways. But let's say when these 3 people are sitting on a round table, so this is your first arrangement. Now let's say we have one more arrangement, that is second arrangement, where second person is sitting here, first person is sitting here, and third person is sitting here. Now third possible arrangement, again first person is sitting here, third person is here, and second person is here. Similarly, for this one, let's say second person is here, third one is here, and second one is here. Now, so this is our arrangement number 4. Then let's say in your arrangement number 5, we have third person here, first one here, and second person here. And let's say we'll have one more arrangement, so third person here, then first here and second here. But if you observe this arrangement 1, 2 and 3, so this is clockwise 1, 2, 3. See, let's observe this one, what we are doing here. So they are sitting 1, 2, 3, that is clockwise. Now here clockwise it is 1, 3, 2. Now here also this is clockwise 1, 3, 2. Here also this is 1, 3, 2. Here it is 1, 2, 3. And here it is 1, 2, 3. So if you observe in case of circular arrangement, somehow we are finding repetitive arrangement in all 6 different cases. So if the arrangement is linear one, then if there are 3 people sitting in linear arrangement, then total number of ways are 3 factorial. But when it is a circular arrangement, at that time we cannot say that total number of possible ways are n factorial. It is always 1 less than n factorial. So here we will fix one person to break the symmetry, and total number of ways in which these n people will sit on the circular table is always equal to n minus 1 factorial. Now here we want two specific people to sit. Let's say they are A and B. Let's have their name as A and B. So we want this A and B specifically to sit next to each other. So here also we need to, unlike that book problem, we have to treat this A and B as a single unit. Hence total number of arrangements will be, now initially it was n minus 1. So n minus 1 minus 1, that is n minus 2 individuals. So total number of arrangements will be n minus 2 plus 1, that is n minus 1 units will be arranged on the round table. Now why we have done this n minus 2 is because we want to treat these two people as single unit. So initially there are n people. So now we have removed these two people. So that's why remaining people is n minus 2. So just assume that let's say there are 20 people and we want this A and B to sit next to each other. So just for the sake of calculation, try to understand the scenario. Let's say we have kept them aside. So we have to arrange remaining 18 people, and these two people we have to consider as one single unit. So 18 plus 1, that's why here it is in terms of n. So first of all we will subtract 2, and then this AB unit we have to add 1. So n minus 2 plus 1, that is ultimately we need to arrange n minus 1 units around the round table. Now in how many ways we can arrange these units? So number of ways to arrange n minus 1 units in a circular arrangement is n minus 1 minus 1 factorial. So if these n minus 1 units are to be arranged in linear way, then it is directly n minus 1 factorial. But we have to arrange them in a circular way, that's why we need to subtract this 1. So n minus 1 minus 1 factorial, that is n minus 2 factorial is the required arrangement. But again this A and B also can swap their places, that's why we have to multiply this n minus 2 factorial by 2 ways. So total number of favorable ways in n of A is 2 into n minus 2 factorial. Now n of A is equal to 2 into n minus 2 factorial. Hence probability of A is equal to n of A upon n of S, that is 2 into n minus 2 factorial upon n minus 1 factorial, that is 2 into n minus 1 factorial upon n minus 1 into n minus 2 factorial. Now this n minus 2 will get cancelled, and we will just have 2 upon n minus 1. So probability of this particular event is 2 upon n minus 1. I hope you have understood this specific variety, that how arrangement in linear way, whenever we need to arrange people to sit in linear arrangement, and in a circular arrangement how it differs. Let's look at example number 12. In a random arrangement of the letters of the word mathematics, what is the probability that all the vowels come together? Previous two problems we have seen of letter arrangement in which there was a scenario where no letter in that particular word was repeated. So this one, example number 8, we have seen, that is the word from the letters of the word article we had to create different arrangements. And second scenario was example number 9, where we had to create different arrangements from the letters of the word failure. But if you observe in both these, example number 8 and example number 9, any letter of the word is not repeated. On the contrary, in this word mathematics, different letters are repeated. So we will check out how to solve this. This is a very classic case of probability where few letters from the word are repeated. In random arrangement of the letters of the word mathematics, what is the probability that all the vowels come together? So first of all, we will identify the letters and their repetitions. Now, how many places are there in this word mathematics? So MATHEMATICS, and S. So there are total 11 letters. Now out of these 11 letters, there are few vowels and few consonants. So let's list down vowels first. A, E, again A and I. So there are total, out of these 11, total 4 vowels we have, and remaining are the consonants, that is M, T, H, M, T, C and S. These 7 consonants are there. So, but out of these 4, 2 vowels are repeated, that is A is repeated, and out of these 7 consonants, M appear twice, T also appear twice. From 11, there are total 6 letters which are repeated, M twice, A twice and T also twice. So first of all, now we will find out total number of possible arrangements. So the total number of ways to arrange 11 letters. See, if there is no letter is repeated in this particular word, then how many total arrangements are possible? That is 11 factorial. But when M, A and T appear twice, M appear twice, A appear twice, T appear twice, that means actually what will happen here is, because of those same letters, those particular arrangements will be exactly same. That's why we cannot consider those similar words. That's why we have to divide these number of repetitions to these number of repetitions are to be divided, and hence that's why total number of arrangements are to be divided with these repetition, and hence n of s is equal to 11 factorial upon 2 factorial for M, 2 factorial for A and 2 factorial for T. So this is our n of s now. Now we will look at the required arrangement. So what we need to calculate here? What is the probability that all the vowels come together? So there are 4 vowels, that is A, E, A and I. That means there are 4 vowels together. So what we need to do now? So these 4 vowels, we need to consider them as one single unit. So in order to find out the arrangement, then there are 7 consonants, and these 4 vowels we need to consider as one block. So how many units we need to make an arrangement with? That is 8 units, one vowel block and remaining 7 consonants. So we have total 8 units now. Hence number of arrangements, let's say here also in these 8 units, if nothing is repeated, then how many possible arrangements are there? That is 8 factorial. But even in this arrangement, M repeated twice and T repeated twice. So total number of possible arrangements is 8 factorial upon 2 factorial into 2 factorial. Now that vowel block also we can have in between arrangement within that vowel block. So in that vowel block, how many vowels are there? There are 4 vowels. But out of those 4 vowels, again A is repeated. So in how many ways we can arrange vowels within this particular block? That is 4 factorial upon 2 factorial. Hence, in what is the total number of arrangement here? That is, in the event where all the vowels come together, should be 8 factorial upon 2 factorial into 2 factorial. So this one and this one. So 4 factorial upon 2 factorial, that is n of a is equal to 8 factorial upon 2 factorial 2 factorial into 4 factorial upon 2 factorial. And now we have to calculate probability. So how to calculate probability? That is n of a upon n of s. So 8 factorial upon 2 factorial 2 factorial into 4 factorial upon 2 factorial whole divided by 11 factorial upon 2 factorial 2 factorial 2 factorial. So let's simplify this. That is 8 factorial upon 2 factorial 2 factorial as it is into 4 factorial upon 2 factorial into 2 factorial into 2 factorial into 2 factorial upon 11 factorial. Now all these 2 factorial in the numerator and denominator will get cancelled. So we have 8 factorial into 4 factorial upon 11 factorial. So let's simplify this now. 8 factorial I will keep it as it is. 4 factorial we will split into 4 into 3 into 2, and 11 factorial we will split up to 8 factorial, that is 11 into 10 into 9 into 8 factorial. Now this 8 factorial will get cancelled. Then we will have this 2 ones are 2, 2 fives are 10, 3 ones are 3, 3 threes are 9. Then we have 4 upon 5 into 3 into 11 is equal to 4 upon 165. So this 4 upon 165 is our final answer. That is the probability that all the vowels come together. This is a very classic case of letter arrangement where few letters from the word are repeated. Let's start with example number 13. A committee of 4 persons is to be appointed from 3 officers of the production department, 4 officers of purchase department, 2 officers of sales department and 1 chartered accountant. Find the probability of forming the committee in the following manner. There must be 1 from each category. It should have at least 1 from purchase department, and the third one is the chartered accountant must be in the committee. Now in previous problem we had solved a specific case of letter arrangement. So by in this video now we have seen some 10-12 examples. In these 10-12 examples I have tried to cover all the specific varieties which are definitely you need to solve whenever you are preparing for the chapter probability. That is a case of coin, a case of dice, multiple dice, then a scenario where you need to choose a specific card from a pack pack of cards. Then we had also solved the problems related to sitting arrangement, linear sitting arrangements as well as circular sitting arrangement. Now in previous problem we have seen how to arrange letters of specific word. This is also a classic case where you need to form a committee from the given set of people. So let's see how to solve this one. Now first of all we will calculate how many total people are available. We need to form a committee of 4 people from, now how many people are available, that is from production department we have 3 officers, then from purchase department we have 4 officers, from sales department we have 2 officers and we have 1 chartered accountant. Now we need to create a committee of 4 people. Let's say first of all we will find out how many possibilities are there in your sample space. So how many total people are there? So what is the value of n is 3 plus 4 plus 2 plus 1, which is equal to 10. That's why total number of ways to choose 4 members from 10 is 10c4. That is n of s is equal to 10c4, which is equal to 10 factorial upon 4 factorial into 6 factorial. So 10 into 9 into 8 into 7 into 6 factorial upon 4 into 3 into 2 into 6 factorial as it is. Now this 6 factorial will get cancelled. This 4 2 and this 8 will get cancelled. This 3 ones are 3 and this 3 threes are 9. So we have 7 into 3 is 21, 21 into 10 is 210. That means how many possible ways are there? That is, value of n of s is 210. Now we'll check out how to find out the first case, that is, there must be one from each department. So that means we need one from production, one from purchase, one from sales, and one from chartered accountant. So we must select exactly one person from each of the four categories. So favorable ways, let's say for this event A, is 3C1 into 4C1 into 2C1 into 1C1, which is equal to 3 into 4 into 2 into 1, which is equal to 24, and hence probability of A is equal to n of A upon n of S, which is equal to 24 upon 210, which is equal to, now we have to simplify this. Let's say I will divide it by 2. So this is 12 and this is 105. Then we can divide it by 3. So 3 4s are 12 and this is 35. So probability of A is 4 upon 35. Now second case is there should be at least one from purchase department. Now here also we will use the complement rule. Wherever you have the case of at least one from at least one case, wherever you will find, it is advisable to solve this with complement rule. So we will find out first that in how many choices there would be none person from the purchase department. That's why probability of at least one we can calculate, that is 1 minus probability of none from purchase. So let's find out first of all probability of not a single person from purchase department. So rest of the department, how many people are there? How many people from purchase department? 4. So out of 10, 4 are from purchase department. So we need to choose 4 people, required 4 people from these remaining 6 people. So ways to pick these 4 people from remaining 6 which are not from purchase department is equal to 6C4, which is equal to 6 factorial upon 4 factorial into 2 factorial, which is equal to 6 into 5 into 4 factorial upon 2 into 4 factorial. 4 factorial, 4 factorial will get cancelled and we will have 5 into 3, that is 15. So we can choose 4 people where nobody is from purchase department in 15 possible ways. That's why probability of 0 from purchase department is 15 upon 210, which is equal to, now 15 you can directly divide 210 by 15. So 15 ones are 15 and this 1 we have 6 and 15 fours are 60. So 1 upon 14. And hence probability of at least 1 is equal to 1 minus 1 by 14, which is equal to 13 by 14 is the final answer. Let's look at the third case, that is chartered accountant must be there in the committee. How many chartered accountant are there? There is only one chartered accountant. So since this chartered accountant must be included, we have already filled one spot. Now we need to choose the remaining 3 members from remaining 9 people. So favorable ways should be 9C3, that is 9 factorial upon 6 factorial into 3 factorial, that is 9 into 8 into 7 into 6 factorial upon 3 into 2 into 6 factorial. So this 6 factorial will get cancelled. This 3 ones are 3 and this 3 threes are 9. This 2 ones are 1 and this 2 fours are 8. So 4 into 3 into 7 is equal to 84, and hence probability of this event B is n of B upon n of S, which is 84 upon 210. You can directly divide this by 21. So 21, 4 and 21, 10, and then 2 2s are 4 and 2 5s are 10. So the final answer of this probability is 2 upon 5. So the chartered accountant must be, what is the probability of chartered accountant being included in the committee is 2 upon 5. I hope you have understood how to solve this committee selection problem. Let's move to example number 14. It is again similar problem. A committee of 4 is to be formed from among 3 economists, 4 engineers, 2 statisticians and 1 doctor. What is the probability that each of the 4 professionals is represented on the committee? What is the probability that the committee consists of the doctor and at least 1 economist? So let's solve this one. Now how many total people are available? That is 3 economists, 4 engineers, 2 statisticians and 1 doctor. So 3 plus 4 plus 2 plus 1, which is equal to 10 again. And a committee of 4 is to be formed. So total number of ways to choose 4 members from 10 is 10C4. Hence n of s is equal to 10 factorial upon 4 factorial into 6 factorial, that is 10 into 9 into 8 into 7 into 6 factorial upon 4 into 3 into 2 into 6 factorial. So this will get cancelled. This 4 2s are 8 and this 3 1s are 3 and this is 3. So 7 into 3, which is equal to 21. 21 into 10 is 210. So n of s is equal to 210. Now let's look at the first case. What is the probability that each of the 4 professors is represented in the committee? Now we have solved exactly similar case in previous problem. So we must select exactly one from each of the 4 categories. So favorable ways is for 3, any one economist from 3 is 3C1, then 4 engineers, so 4C1, 2 statisticians, that's why 2C1, and 1 doctor is 1C1, that is 3 into 4 into 2 into 1, which is equal to 24. So probability is equal to probability of this event n of a upon n of s, which is 24 by 210, and after simplification you will get the answer as 4 upon 35. Let's look at the second case. What is the probability that the committee consists of the doctor and at least 1 economist? Now there is 1 doctor and how many economists are there? 3 economists are there. Now we had already seen that whenever you have the word at least in your selection process, you should use the complementary use. Now in this case we need to choose at least 1 economist, but we also need to choose doctor. How many doctors are there? 1. So in this scenario the doctor is always fixed, that is only one way of selecting a doctor. Now we need to fill remaining 3 spots such that there is at least 1 economist always. So it is easier. See, we need to select 4 people. Out of 4, doctor is always fixed. So remaining 3 spots we need to select in such a way that there is always at least 1 economist. So you can have at least 1 economist, 2 economists, or all 3 economists. So that's why it is easier to calculate that using the complement for the remaining 3 spots. So total number of ways to fill these 3 spots from 9 people. Now why 3 spots and 9 people? Because we had already filled 1 spot by the doctor. That's why now we don't need to select 4 spots, but we need to select only 3, and there were total 9 people, but doctor was already selected. So and there is only 1 doctor. So we need to fill these remaining 3 spots or remaining 3 places with remaining 9 people only. That's why total number of ways to fill these 3 spots from 9 people. But here one more condition is added, that we cannot choose any economist because we are using complementary approach. So total number of ways to fill these 3 spots. So n of s in this case we need to calculate. So what is this n of s? That is 9c3, which is equal to 9 factorial upon 3 factorial into 6 factorial, that is 9 into 8 into 7 into 6 factorial upon 3 into 2 into 6 factorial. So 6 factorial will get cancelled. Then this 3 and this 3 you will have. This is 2 and this is 4. So 4 into 3 into 7, which is equal to 84. Now we need to find out in how many cases there is no economist. So how many remaining people are there except economists? Now there are 4 engineers and 2 statisticians, that is 6 people are there. So ways to choose these 3 people where no economist is involved is equal to 6C3, that is 6 factorial upon 3 factorial into 3 factorial. So 6 into 5 into 4 into 3 factorial upon 3 into 2 into 3 factorial. So this 3 factorial will get cancelled. This 6 and this 6 will get cancelled. So we just have number of ways as 20. Now favorable ways for the 3 spots is equal to now 84 minus 20. So initially we had 84 to total ways by which we can fill these 3 spots is 84, out of which the case in which there is no economist is 20. That's why favorable ways in which at least one economist is there, that is 84 minus 20 is equal to 64, and this is doctor is already there in only one way. So the total probability of this case is 64 upon 210. So n of total number of possible ways for this event is 64 and n of s is 210. So 64 upon 210 is equal to 32 upon 105. So I hope you have understood this case as well. Let's move to example number 15. A card is drawn from a well shuffled pack of 52 cards. Find the probability that it is either a diamond or a king. Now here it is either a diamond or a king. So we need to pay attention to this word or. So which we need to choose only one card, but that card can be either a diamond or a king. Now you can easily find out how the probability of choosing a diamond, that is how many diamond cards are there? 13. So 13 by 52. Or maybe a king. So how many kings are there? 4. So 4 upon 52 and so on. But here it is either a diamond or a king. So when drawing a card from a 52 cards, the total number of ways to choose the card is given by the combination formula, that is 52 NCR is equal to 52 C1, which is equal to 52. Hence n of s is equal to 52. To find the probability that the card is either a diamond or a king, we have to use addition theorem, that is addition rule of probability. Why we have to use this? Because there is a diamond and a king. Whenever we need to choose a diamond or a king, then there is one diamond king which is overlapping in both the cases. So we have to use this addition theorem, that is probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. So now which is event A? So let's say event A is the card is a diamond. So how many diamonds are there? 13. Hence n of A is equal to 13. And what is event B? Event B is that particular card is a king. So how many kings are there? There are 4 kings. Hence we can say that event probability n of B is equal to 4. Now we need to find out how many possible outcomes are there in A intersection B, that is how many common events are possible. Now there is exactly one king which is a diamond as well as king. That's why n of A intersection B is equal to 1. Now as n of A is 13, so probability of A is 13 by 52. N of B is 4, hence probability of B is 4 by 52. N of A intersection B is 1, hence probability of A intersection B is 1 by 52. when we need to find out the probability of it is either a diamond or a king. So whenever there is an or word, we need to use the rule of addition. That is, it is either a diamond or a king. So probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. Now why we need to subtract this is because this common part is already counted in event A also and event B also. So we need to subtract it once so that it will not get counted double. That's why now 13 plus 52 plus 4 plus 52 minus 1 by 52. Now see, when in the previous step we had calculated probability of A, B and A intersection B, the answers were 13 by 52, 4 by 52 and 1 by 52. Although we can here only simplify this 13 by 52 as 1 by 4 or 4 by 52 as 1 by 52, I had specifically not simplified them into the best fraction, so that now it will help us for easy calculation. So 13 by 52 plus 4 by 52 minus 1 by 52. So the denominator is already 52. That's why our calculation is easy. We don't need to take LCM. If we had simplified this to 1 by 32 or 1 by 13 and 1 by 52, then again we need to repeat this step of taking LCM. That's why I had not done this. So this is a pro tip whenever you are solving calculation problem, that whenever you need to convert any fraction to decimal or best fraction, always do this simplification and for your final answer only. For in between steps, don't do it, so that your calculations will be easy. Now 13 plus 4 minus 1 is equal to 16 by 52, and as now 16 by 52 is your final answer, you can convert it to the simplest fraction, that is 4 upon 13. Hence probability that it is either a diamond or a king is how much, which is 4 by 13. So 4 by 13 is your final answer. Let's move to example number 16. If probability of A is equal to 0.4, probability of B is 0.7 and probability of at least one of A and B is equal to 0.8. Find the probability of only one of A and B. Now let's try to understand what is the terminology used here. Probability of A is 0.4 and probability of B is 0.7. It's already given that probability of at least one of A and B. Now it is at least one of A and B. That means you can have either A or B, or you can have both A and B, and hence at least one of A and B is nothing but your probability of A union B. That's why probability of A union B is already given, which is 0.8. Now with the help of addition rule, we can find out probability of A intersection B, that is 0.8 is equal to 0.4 plus 0.7 minus probability of A intersection B. So 0.8 is equal to 1.1 minus probability of A intersection B. So probability of A intersection B is equal to 1.1 minus 0.8, which is equal to 0.3. Now what do you mean by A intersection B? Is the common part of A and B. But what we need to calculate is probability of only one of A and B. A intersection B is always A and B. See, try to understand the terminology and the mathematical part of this. So whenever we want A or B, it is always A union B. Whenever we want A and B, it is always A intersection B. And now here we need to find out probability of only one of A and B. So only one of A and B refers to the case where if A occurs, then B does not, or if B occurs, then A does not. That means what we need to find out, that probability of only one. So actually by only one you can find out probability of any one minus probability of both together. That's why probability of only one is equal to probability of A union B minus probability of A intersection B, which is equal to now 0.8 minus 0.3, which is equal to 0.5, and hence probability of only one of A and B is equal to 0.5. Let's move to example number 17. A chartered accountant applies for the job in two firms, X and Y. He estimates that probability of his being selected in the firm X is 0.7 and being rejected at Y is 0.5. The probability of at least one of his application being rejected is 0.6. What is the probability that he will be selected in one of the two firms? Now first of all we will write down whatever things are given in the problem. Let's say there is an event X that particular chartered accountant is selected in the firm X, and event Y is that the CA is selected in the firm Y. Now it is given that he estimates that probability of his being selected in the firm X is 0.7, hence probability of X is 0.7. Then it is also given that his being rejected in firm Y is 0.5. Now what is event Y? That he is selected in the firm Y, but it is given that probability of he being rejected at Y. Hence we need to consider the complement event of Y. So being rejected, that means probability of Y complement is equal to 0.5. But we are aware probability of Y plus probability of Y complement is always equal to 1. Hence we can find out probability of Y is equal to 1 minus probability of Y complement, that is 1 minus 0.5, which is equal to 0.5. So probability of X is 0.7 and probability of Y is 0.5. Now it's also given that the probability of at least one of his application being rejected. Now at least one of his application, that means his one application can be rejected or both the applications can be rejected. For rejection we need to take complement event, and one or it is two, that is both the applications, hence we need to take union event. So probability of X complement union Y complement is equal to 0.6. Now what we need to find out is what is the probability that he will be selected in one of the two firms. So we need to find out one of the two firms. So let's say first of all we will find out probability that he is selected in both the firms. Both the firms, that means X intersection Y. So now we are already given with the probability of X complement union Y complement. So we will use De Morgan's law here, and what this De Morgan's law says is probability of X complement union Y complement is equal to 1 minus probability of X intersection Y, that is 0.6 is equal to 1 minus probability of X intersection Y. That means probability of X intersection Y is equal to 1 minus 0.6, which is equal to 0.4. That means probability of he being selected in both the firms is 0.4. But what we need to calculate is what is the probability that he will be selected in one of the two firms. So we need to find out one of the two. That means either he should be selected in X or he should be selected in Y only. The phrase selected in one of the two usually implies at least one. However, if the intent is exactly one, we need to calculate this differently. So there is a first case that he is selected in at least one firm. So at least one, that means X union Y. that is equal to probability of x plus probability of y minus probability of x intersection y, which is 0.7 plus 0.5 minus 0.4, which is equal to 0.8. And case B, probability of he being selected in exactly one firm. So this is the probability of he being selected in x or y but not both, that is probability of exactly one, is equal to now probability of x union y minus probability of x intersection y, and for this we had calculated x union y also, that is 0.8 minus 0.4, which is equal to 0.4. So probability that he will be selected in one of the two firms, that is exactly 1, is equal to 0.4 is your final answer. Let's quickly look at example number 18. Probability that a man will be alive for 25 years, hence is 0.3, and the probability that his wife will be alive 25 years hence is 0.4. Find the probability that 25 years hence both will be alive, only the man will be alive, only the women will be alive, at least one of them will be alive, and none of them will be alive. So what is the event given here? Probability that a man will be alive. So let's say we have an event M where man is alive for 25 years, hence, and event W that his wife will be alive for 25 years. Now what is given? Probability that a man will be alive, that is probability of M is 0.3, and his wife will be alive for 25 years is 0.4. So probability of M is 0.3 and probability of W is 0.4. Now we need to find out the probabilities that both will be alive and etc. So first of all we will find out probabilities of complement event. P of M is 0.3, hence probability of M complement, that is the man won't be alive, is equal to 1 minus probability of M is 0.7, and similarly probability of W complement, that is women won't be alive, is 1 minus 0.4, which is equal to 0.6. Now let's look at the first case, that is both will be alive. Since the events are independent, we multiply the individual probabilities because probability of man and women alive is not dependent on each other, and hence probability that both will be alive, that is M intersection W, but there is nothing common, hence M intersection W is equal to probability of M into probability of W, that is 0.3 into 0.4, which is equal to 0.12. Now second case, only the man will be alive. So we want the event that M is alive but W complement we need to consider here. That means the man is alive and his wife does not. So probability of M intersection W dash. Now this is also independent event. So we need to multiply probability of M into probability of W complement, which is equal to 0.3 into 0.6, which is equal to 0.18. Let's look at the third case, that is only the women will be alive. Now similarly we need to consider that women is alive and man does not. Hence probability of M complement intersection W, that is probability of M complement into probability of W, which is equal to 0.7 into 0.4, which is equal to 0.28. Let's look at the fourth case, at least one of them will be alive. Now at least one of them, hence we need to consider the probability that we need to consider the complementary event. So M union W, that is at least one of them is alive. So M union W is equal to probability of M plus probability of W minus probability of M intersection W, that is 0.3 plus 0.4 minus 0.12 is equal to 0.58. And fifth case is none of them will be alive. That means wife is also not alive and man is also not alive. Hence probability of M complement intersection W complement is equal to probability of M complement into W complement. So 0.7 into 0.6 is equal to 0.42, and hence this is how we can calculate probabilities of intersection of event whenever two events are independent. So if you have independent events, then intersection is to be calculated by multiplication of the events. Let's look at example number 19. The probability that a management trainee will remain with the company is 0.6. The probability that an employee is earning more than 10,000 per month is 0.5. The probability that an employee is a management trainee and who remain with the company or who earns more than rupees 10,000 per month is 0.7. What's the probability that an employee earns more than 10,000 given that he is a management trainee who stays with the company? Now whenever you have this word given that means this is a case of conditional probability. So whenever we have this given that word, that means it is a case of conditional probability. Now let's define an event first. The probability that management trainee will remain with the company. So let's say we have an event A, that is the employee is a management trainee who remains with the company, and it is given that the probability of this event A is 0.6. Now there is a second event. The probability that an employee is earning more than rupees 10,000 per month is an event B, and probability of this event B is given as 0.5. Now what next is given? The probability that an employee is a management trainee and who remain with the company or who earns more than 10,000 per month is 0.7. So probability of A intersection B, that is the employee is a management trainee who remains with the company or earns more than rupees 10,000. Now here there is a word or. So probability of A union B is given, which is 0.7. A intersection B is not given. A union B is not given because there is this word or. Now we will find out probability of A intersection B. So addition rule, probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. So 0.7 is equal to 0.6 plus 0.5 minus probability of A intersection B, that is probability of A intersection B is equal to this 1.1 minus 0.7, which is equal to 0.4. Now probability of A intersection B is 0.4. That means probability of that particular employee is a management trainee who stayed with the company as well as he is earning more than 10,000 rupees is 0.4. But what we need to calculate here, what is the probability that an employee earns more than 10,000 given that he is a management trainee? So we need to calculate conditional probability. So the question asks for the probability that an employee earns more than 10,000. More than 10,000 is event B, given that he is a management trainee. So this is an assumed condition. So event A is an assumed condition. That means we need to calculate probability of B upon A. So whichever is the given condition, that should come in the denominator. So probability of B upon A is equal to, now the formula, probability of A intersection B upon probability of A, whichever is in the denominator, that probability you need to consider in the denominator. Now A intersection B we had just calculated 0.4. Probability of A is already given. So 0.4 upon 0.6 is equal to 2 upon 3. So 2 upon 3 is the final answer in this question. Let's start with the example number 21. Here the table is given. To factor factories manufacture the same machine part, each part is classified as having 0, 1, 2 or 3 defects. The joint probability distribution for this is given below. So number of defects 0, 1, 2 and 3, and there are two manufacturers, manufacturer A and manufacturer B. So for manufacturer A, 0 defects probability is 0.1250, 1 defect 0.0625, 2 defects 0.1875 and 3 defects 0.1250. For manufacturer B, for 0 defects 0.0625, for 1 defect 0.0625 again, for 2 defects 0.1250 and for 3 defects 0.2500. And what all things you need to calculate is, a part is observed to have no defects, compute the probability that it was produced by manufacturer B. A part is known to have been produced by manufacturer A, compute the probability that the given part has no defects. A part is known to have 2 or more defects, compute the probability that it was manufactured by A. And the fourth question is, a part is known to have 1 or more defects, compute the probability that it was manufactured by B. So the data is given in terms of table, that is multiple events are given, and we need to calculate these 4 probability for these 4 cases. Now first of all, what we will do is we will complete the table by calculating the total probabilities. So let's say how much is the total probability given, that is total weightage given for manufacturer A. We will calculate the total of probability of 0, probability of 1, 2, 3 and 4 for this particular. So let's say this total is equal to 0.5 and this total is also 0.5. That means we can say that manufacturer A and B are having equal weightage, 0.5, 0.5. Now we will also calculate these totals, that is total probability of having 0 defects is 0.1875, total probability of having 1 defect is 0.125, total probability of having 2 defects is 0.3125 and total probability of having 3 defects is 0.375. Now we'll look at each question. So let's say I have taken down the table here. So the first question is, a part is observed to have no defects. No defects means 0 defect. Compute the probability that it was manufactured by manufacturer, it was produced by manufacturer B. Now for 0 defects, how much is the probability of manufacturer B is this part, that is 0.0625. And what is the total probability of having 0 defects, that is 0.1875. Hence probability of having 0 defects by manufacturer B is equal to 0.0625 upon 0.1875, which is equal to 1 upon 3. See here, you don't need to make any calculation, rather you need to be very good at understanding and decoding the table. That is the only crux of this particular problem. Now let's look at the second scenario. A part is known to have been produced by manufacturer A. Compute the probability that the part has no defect. Now exactly similar to this, that is no defect, that means 0 defect from manufacturer A. So 0.1250 and total probability of having 0 defects is 0.1875. So probability of 0 defects and the part is manufactured by A is 0.1250 divided by 0.1875 is equal to 2.2 by 3. Let's look at the third case. A part is known to have 2 or more defects. Compute the probability that it was manufactured by A. Now 2 or more defects, that means in the numerator we will have summation of these 2, that is 0.1875 upon 0.1250, and in the denominator that is sample space, we need to have total probabilities of having 2 or more defects, that is 0.3125 plus 0.375, which is equal to 0.3125 upon 0.6875, which is equal to 5 by 11. And let's look at the fourth case. A part is known to have one or more defects. Compute the probability that it was manufactured by B. Now, one or more defects, that means we need to consider one defect, two defects, or three defects. So, one defect, two defect, or three defect, that is 0. So, this is probability of 1 plus. So, 0.0625 plus 0.1250 plus 0.25 upon, now this total of 1, 2 or 3 defects. So 0.125 plus 0.3125 plus 0.375 is equal to 0.4375 upon 0.8125, which is equal to 7 by 13 is the final answer. So this is just about understanding of the given data. Let's look at problem number 22. Again, similar case, we have the data from 100 economists in academic, private sector and government concerning their opinions whether economy would be stable, expand or contract in near future. However, a part of the information was lost. Now the table is given for economist and academician, private sector R and government G, and for stable we have 25 academicians and 5 government. Total is given as 40. For expanding there are 7 private sectors and 8 from government. For contracting 20 academicians and total is given for private sector it is 22 and for government it is 13. Based on the remaining data, you are required to create probability table. From the given table, find out probability of A, probability of E, probability of A intersection E, probability of G intersection C, probability of E by G and probability of G upon E. So in this case, first of all, we have to complete this table. So let's see how we can do it. Now here, let's look, we can complete the table in specific sequence. So first of all, consider this particular row. Now here 25 was given, 5 was given and total 40 was given. So from this we can calculate 25 plus 5 is equal to 30 and 40 minus this 30 is equal to 10. So we can find out that there are 10 employees from the private sector. Now similarly, in this government row, it was given that there are 5 plus 8 and 13 total was already given. So we can find out that for contracting, that is 5 plus 8 plus let's say x is equal to 13. That means for contracting there are just 0 people. Now this total data is for 100 people. So we can write this 100. Now let's say the total academicians we are not aware. So let's say it is x. Then x plus 22 plus 13 is equal to 100 and from that we can find out the total academicians as 65. Now let's consider the first row, that is 25 plus x plus 20 is equal to 65. From that we can find out that expanding academicians is 20. Now let's say we consider this particular column. So now 20 plus 7 plus 8. So total of government is 35. Now we are left with only one entry. This is this one. So 40 plus 35 plus x is equal to 100. That's why this contracting total is 25 and this 5 is already there. So 20 plus 5 plus 0 is equal to 25. You can also cross check. So we had all the values in this table and now we will calculate the probabilities for given scenario. So let's copy the table here. Now the first one is probability of A. So that how many total academicians are there? 65. So probability of A is 65 upon total 100, which is 13 by 20. Then probability of E. Probability of E. How many total expanding is there? 35, so 35 upon 100 is 7 by 20. Then probability of A intersection E. A intersection E is how much? This part. So A intersection E is 20, so 20 upon 100 is 1 by 5. Then probability of G intersection C. G intersection C is this particular entry, which is 0. That's why probability is also 0. Now we need to calculate probability of E upon G is equal to probability of E intersection G upon probability of G. So what is E intersection G? How much is it? E intersection G is 8 and probability of this G is, total G is 13. So 8 upon 13, and probability of G upon E is probability of G intersection E, which is equal to 8 again, and probability of E is 35, so it is 8 upon 35. So this is also about only completion of your table, completion of the correct entries, and you just need to find out relevant entry from the table. Let's look at next problem. A sales manager is setting targets for the company and is speculative about meeting targets or practical achievements. From 40 years of his experience in setting targets, he has deduced that chances of achieving target between 60 and 79% of set value are 3 times as good as those of achieving between 80% to 99% of set value, and 1.5 times as good as those of achieving between 30 to 59% of set value. Finally, full target has been achieved only twice during his tenure, and the manager doesn't expect the pattern to change. Find the probability of achievement. Now here the problem statement itself seems very big. So first of all, don't worry about how big that problem. Although the problem statement is very big, trust me, it is very simple to solve. So we will jot down all the given things step by step. So here a sales manager is setting up targets for his company and is speculative about meeting the targets or partial achievement. Now in this question, what they have asked you is, finally full target has been achieved only twice during the year, and we need to find the probability of achievement of specific target. So probability of that particular segment we need to find out. So first of all, we will identify all the events and all the variables. So let's define the probabilities of the 4 ranges of achievement as mentioned in the given problem. Now consider the last statement, finally full target has been achieved only twice during his tenure, and it's also given what is his total tenure. His tenure is 40 years. So let's say we have an event A, that is full target, 100% target is achieved. So this has happened twice in 40 years. Now let's say we have an event B, that is 80 to 99%. So now this probability we will assume as, let's say, X. Then there is an event C where 60 to 79% target is achieved, and there is an event D where 30 to 59% of the target is achieved. Now we will write down all the probabilities. So let's say from the 40 years of experience in setting targets, he has deduced that chances of achieving the target 60 to 79% of set values are 3 times as good as. Now 3 times of what? So this 60 to 79% is 3 times of something. Now 3 times of what? As those of achieving 80 to 99%. So now let's say for 80 to 99% we will assume the probability as X. Now if probability of this event B is X, then for event C it should be 3 times, that is 3x. Now it's also given that and it is 1.5 times. See, I'm here. So 1.5 times as good as of achieving between 30 to 59%. So this event D is equal to 3x divided by 1.5. So for event C, if it is 3x, then event C is 1.5 times of D. Hence probability for event D is 3x upon 1.5, that is 2x. So we have probability of event B, C and D also. And probability of A is already given, that is twice in 40 years. So 2 upon 40 is equal to 0.05. Now we are aware that summation of all the probabilities in the sample space is always equal to 1. So in this complete solution, we just have to use only this rule, that is summation of all the probabilities in the sample space is equal to 1. So create the equation properly and put all those values, that is probability of A, probability of B, probability of C and probability of D is equal to 1. So probability of A is 0.05, then plus x plus 3x plus 2x is equal to 1. Now let's solve this equation for x, that is 0.05 plus 6x is equal to 1. So 6x is equal to 1 minus 0.05, which is equal to 0.95, and hence x is equal to 0.95 divided by 6, that is 0.1583. And from this we will find out all the probabilities, that is x, value of x is 0.1583, and we need to find out probability of 60 to 79%, which is 3x, and hence 3 into 0.1583, which is equal to 0.4749, and this is your final answer, which is approximately equal to 0.475. Let's look at one more problem. Let's look at one more similar problem. A teacher is setting up a question paper for students and speculate about percentage of students who pass the exam from 10 years of his experience. He had deduced that chances of percentage of pass students to be between 75 and 99% are twice as good as of percentage of pass students between 50 to 74% and 2.5 times as good as percentage of pass students between 25 and 49%. Finally, all the students have passed only once during his 10 years and teacher doesn't expect the pattern to change. Find the probability that students between, so basically for all the 4 slabs we need to find out the probability, that is 0 to 24%, 25 to 49%, 50 to 99% and 100%. Now here also first of all we will identify the events and respective variables. So let's define the probabilities for various passing percentage. So let's say we have an event A where 100% passing percentage is there. Now it is given that this 100% passing occurred only once during 10 years. So probability of 100% is 1 by 10, which is equal to 0.1. Now event C, let's say we have an event C where passing percentage is 50% to 74%, which is event B is twice as good as this. That's why if we assume probability of 50 to 74% x, then for event B, that is 75 to 99%, the probability should be 2x. And for the event D, that is 25 to 49%, event B is 2.5 times as good as this. So for event D, probability is 2x upon 2.5, that is 0.8x. So just read the information which is given in the problem carefully and create the equation. Now here event E, that is 0 to 24%, is not given. That's why we should not consider this. Now probability of all the events in the sample space. Total probability of all the events in the sample space is 1. So summation of all probabilities in the sample space must be equal to 1. Hence probability of 100% plus probability of 75 to 99% plus probability of 50 to 74% plus probability of 25 to 49% is 1. Hence 0.1 plus 2x plus x plus 0.8x is equal to 1. So 0.1 plus 3.8x is equal to 1. 3.8x is equal to 0.9, and hence x is equal to 0.9 divided by 3.8. So x is equal to 0.2368. And now from this we need to find out probabilities of all the respective events. So let's say we will create a table. So 0 to 24%, it's not given, so we will just write 0. Now 50 to 74% probability is x. We had assumed that as x, so the required probability is 0.2368. Then for 25 to 49% it is 0.8x, that is 0.2368 into 0.8, which is equal to 0.1895. And for 75 to 99% it is 2x, that is 0.2368 into 2, which is equal to 0.4736. And for 100% it is already given that it's a 0.1. Now you can always cross check whether our calculation is correct or not. So just cross check the summation of these values should be exactly equal to 1. Now here if you do the summation, we are getting the value as 0.9999, which is approximately equal to 1. That's why we can say that our calculation is correct. Yes, and now we had covered almost 24 problems, from simple dice rolls to complex joint probability distribution. If you made all the way to end of this video, congratulations. You now have a solid foundation, this is my guarantee, for your business statistics computational mathematics for probability chapter. Remember, probability is not about memorizing formula, but it's about understanding the logic of how events relate to one another. I have specifically chosen these problems to align with BBA, BCA, BSC and MBA syllabus to make sure that you go back and try a few of these problems on your own without looking at the solution. If you got stuck on a specific section like the committee section or maybe the word arrangement, feel free to rewind and watch that particular part again. If this video helped you to clear your doubts, please give me a thumbs up and subscribe to Amrutasblink. It really helps the channel grow and allow me to keep creating these educational resources for you. And I would like to hear from you. Comment below and let me know which topic you want me to cover next. Thank you so much for learning with me today. Keep practicing and I would like to see you in next video. Bye.